Again, good morning. Warm welcome to everyone for the day 2 of the summit. It's our distinct pleasure to have Professor Alexander Wong, who is a professor in the Department of System Designs Engineering at the University of Waterloo. He also co-directs the Vision and Image Processing Lab, as well as he is the Canada Research Chair in AI and Medical Imaging. And also is a serial entrepreneur, as he co-founded DarwinAI and and other things. Is a CV, you can look at his CV in the program. We are so fortunate to have Professor Wong here, and we look forward to his plenary talk. Thank you so much, Alex.
Perfect. So am I speaking too loud or for echo? Okay. Okay, perfect. So thank you again for this, I guess, opportunity to talk about some of what I do. It might seem a bit different than what you've been hearing in other talks, but hopefully there's something here that you find interesting, exciting, and potentially useful in your particular area. So today, what I'm going to talk about is more on the theme of intelligent design through explainability and trusted AI-driven design for healthcare. So what on earth do I actually mean by this? So first of all, I work in the area of artificial intelligence, right? In particular, machine learning, deep learning, so on and so forth. And so there's been huge amount of advances in artificial intelligence that a lot of times that we're not aware of. So for example, if you take a look at this article, it was actually very viral, not too long ago, right? It's a self-help article talking about, when you're feeling unproductive, maybe you should stop overthinking. A lot of people read this article. They actually felt really good. They thought, wow, this is really a great piece, got great advice, great insights into it, and it helped them, live better, right? But what they didn't know, and what they found out later, they felt a little cheated, was this entire article was written by an AI, right? A machine that, pretends to be able to write, right? So this is a very large scale language model, and yet it's able to generate something that I would say writes better than I do. And that's just one part of the equation. Sorry about that, just a little stuck. And so there's been actually a lot of other advances and promises in artificial intelligence that we might not be aware of, but has actually been really pushing the field into everyday use. So a good example is the one I just mentioned relates to natural language processing. The ability to ingest a huge amount of text and then be able to create something that might even potentially be creative. All right, they've done this for text. They've also done it for images. You can literally type "a dog is eating corn sitting at the beach," and it'll automatically generate that for you. So it's actually really incredible. The ones that we're more familiar with has been on visual perception, right? Self-driving cars, the ability to have sensors that sense all around you, be able to actually reconstruct the entire scene so it knows where to drive, where to steer. And on the bottom right is something that you're so used to that you don't even think of it as AI anymore. Right? Which is when you're, typing that email or sending that text, and it automatically completes it for you. A lot of times incorrectly, but in most general cases, it could actually complete most emails in a very coherent fashion. And so you're used to AI every day. So it's working. So we're no longer at that stage where we're wondering, okay, will AI work for this? Well, it actually does work. But then what is the problem? Why don't we see it all the time? Well, people are starting to now migrate it to healthcare realm. Right? So on the top, what you see is an example of what I've done, which is leveraging AI for clinical decision support. So the ability to actually not just show the clinician or radiologist, what is wrong with the patient, but also give recommendations, diagnosis, as well as help them focus on different areas. And this kind of technology has been actually leveraged in a wide variety of different commercial products that you might not be aware of. So for example, it's integrated into like Siemens AI RAD Companion, Agfa Ruby for AI. So doctors are actually using this type of technology right now to help with their diagnosis, right? On the top right is what we call discovery radiomics, which is in the old days where people try to do handcrafted features saying, okay, this might be important, that might be important, and then try to encode it and using that to create kind of like a DNA for a particular patient's condition. But to handcraft that is actually very difficult. So what we've done is taken away that automatically learns from all this data, to essentially create what we call a radiomic sequencer to then allow you to discover what is the most important signs within an image, within a genetic sequence, and so on and so forth, that allows us to characterize that particular disease. And of course, there's been a lot of research going on in drug discovery, which is given mass amounts of data based on target molecules, how they interact, and so on and so forth, as well as patient response. What we can then do is take all that and learn and identify what is the best target molecule, even down to the patient level. So that's where AI-powered personalized medicine really comes into play. So everything sounds good and all, but perfect. Sorry about that. So what we've done is we continue in taking this and we try to expand it at a different level, right? So you see a lot of commercial products and so on and so forth, but a lot of times you don't really understand how they work, and it's not really accessible to a lot, especially in developing countries. So what we've done is we try to make this all open AI initiatives available to everyone. And one of our first starting points was COVIDNet, which is a global deep learning initiative, right, for COVID-19 clinical decision support. It's open source, open access. We've given every single piece of information, data, algorithm out for the world to use for free. You could go to that website, and not only that, we also go with kind of like a software model where we continuously improve. So we have regular releases of data, new models, because especially for a pandemic, things change over time. And so models need to update based on the changing conditions as with the data. Started between myself and my former student. It was just a team of 2. Now we have pretty much close to 100 different people around the world working on this. We're actually very helpful. It's the most widely used open AI models of its kind for COVID-19. And it's now used across all continents, which we're actually very happy about. We actually found out there was a particular case where I can't say which government, they're actually using that, and they're flying helicopters to different areas, remote areas, and using this to help screen patients. So we're actually very happy about that. So we started off with just detection, risk stratification, but now it covers a much broader range of the clinical decision support, right? Ranging from diagnosis to prognosis, risk stratification, triaging, all the way down to treatment planning. And so we've received a lot of global support as well as media coverage. We're actually very happy that people actually like to use our research, right? As a researcher, that's the most gratifying part. Okay, so just a really quick, overview of this before I get into one of my main topics is that we've made all these models available to everyone. There's 8 different initiatives within this broader COVIDNet initiative. We have our COVIDX, which is the open access benchmark data set available to everyone. We have models for, SARS-CoV-2 detection from chest X-rays. We have severity assessments. We have, ones for computed tomography, like CAT scans, for ultrasound. We're now also getting into biochemical information. So being able to infer survival prediction, as well as acute kidney injury predictions for COVID-19 positive patients, using the clinical, imaging, and biochemical markers. And we've wrapped all this within something we call COVIDNet ML-Sys, which allows you, a doctor, to be able to plug it directly into their clinical system and use it within their workflow. Right? So we're very happy that people are using it right now, and we're continuing to improve it, especially in the response part. So what action should be taken on the patient, as well as what treatment should they get, and how effective that might be. So in addition to open models, we also have open data available to everyone. So we created COVIDX, which is the largest open access data set of its kind. We have data from more than 17,000 patients. Might not seem that much given the number of people who have it, but to be able to make this available open to everyone is actually very, very challenging. We have the data in countries, and the most important part is diversity. We have at different views, we have at different imaging systems, portable, fixed, different positions, supine, upright, across gender, age, demographics, because diversity is very important, and getting it with different modalities, so imaging, clinical data, biochemical data, and so on and so forth. And this allows AI models to learn much better, right? You don't want to learn an AI model that's extremely biased towards just one demographic. you want it to be able to generalize well across all the populations. And so we're quite happy about that. I think my happiest about this was I was at a conference, and then a couple students came up to me and said, hey, you know, we're able to actually finish our thesis because we had access to this data. So I think the big question is, like, this all sounds great, right? I could be one of those AI people, evangelists, and just go around and say, AI, you know, can solve all the world's problems, but I don't do that, right? So the question that we want to really think about is, why don't we use AI all the time right now? And having worked with extensive collaborations with different enterprises in automotive, transportation, aerospace, finance, agriculture, healthcare, and so on and so forth, you know, at first, there's a common message across all the industries as to why don't they use it right now. What they found is that AI, especially deep learning, can be very game-changing, but it's full of challenges to widespread adoption across industries. So translating from promise to impact has been a big problem. And one of the biggest challenges they face right now in real-world practice, especially in healthcare, is trust. Can you trust this AI solution that somebody has built, right? And that's where reality sets in. So I always like to use this example because I always find it fun. It actually got quite viral a while back. So here's an example of a football game, soccer game, however you want to call it, right? People playing, nothing special about it. But what happened was people were complaining, right? Throughout the entire live stream feed, all it did was stare at not the players, not the ball, but the referee's bald head, right? And what they found, right? Again, this is AI in the wild. Things don't always work out in the wild. Is that it thinks the bald head is the ball, and so it tracks it perfectly, like awesome bald head tracking, but terrible for capturing the action. And so that's where trust starts breaking when using AI in the wild, when it's not created and tested properly, right? And of course, that's funny. Here, it's not as funny when trust breaks, especially in the healthcare system. A good example is this story that came out, article that came out on the left, right? Where what they found was that this AI system that was used to look at hundreds of millions of people in the US to determine what kind of treatment they should get actually had an inherent bias, a racial bias, right, against a certain demographic, right? This is the thing that decides whether somebody gets a certain type of treatment. It's a big deal. And yet it had huge inherent biases. And so they, like, researchers dug deeper into it. And what they found was, guess what? An AI is only as good as its data. It's like when you're teaching a child something. If you teach a child a certain way, they will think it's correct, whether it's actually correct or not, right? And so what they found was, historically, more money was spent on Caucasians, right? Therefore, the AI thinks we should spend more money on them, right? So that's the kind of mentality. It's a logic, like you understand how it came to the conclusion, but it's not right, right? And so that causes a problem. And more recently, there are situations where now it's not even just accidents. People are actually trying to maliciously attack AI systems. So a good example is on the right, where people have been looking at adversarial attacks, right? So things that you think from cybersecurity, like data poisoning and so on and so forth, they're now trying to apply to clinical data. So here you might have a situation where a person is perfectly fine, but if the hacker attacks the image just right, you cannot actually see the difference. So you take a look at the original image and the adversarial example, to your eyes, they look identical. But one will say it's benign. The other one says is malignant, right? You don't see it. How the AI picks up this data poisoning and changes the decision accordingly. So where can it be used for malicious purposes? Where does it lose trust? People have been thinking this can be used as a way to cheat the system, the healthcare system, out of money. Because then you could force them to prescribe a certain drug, and that drug usually would not be accessible. And so these are the kind of things that start getting you to think about, when trust breaks down, can you really, like, would a clinician really want to use it within the healthcare system? Right? And nowadays, before, people were always thinking, we'll wait and see. When it happens, then we'll worry about it. When people stop trusting it, well, there's no longer wait and see. There's actually regulatory consequences coming up. So there's the Canadian Digital Charter, C11, right, for algorithmic transparency. The European Commission's AIA Act, which finds up to 30 million euros or 6% of global revenue. That's a lot of money, right? The FTC has been telling people that you better hold yourself accountable when using AI or be ready for FTC to do it. So compliance is now a global must. So this all sounds very grim. So what that kind of tells you is like, never use AI for anything real, right? The answer is no. There's actually a lot of advances in research labs, in companies, and so on and so forth towards ethical, responsible, trust-driven design of AI. That's where the intelligent design based around trust and explainability really comes into play. So things I'm going to talk about here related to this idea of intelligent design based on trusted AI centers around quantitative explainable AI. Why did the AI make a decision the way it did? Doesn't matter for healthcare or not. This is critical in all mission critical systems, or even for scientific discovery. Why did it say I should do this? Why did it predict that this would happen? Then we have trust quantification, which is when can an AI be trusted and where are the gaps and biases in its fairness? Then we talk about improved medical imaging modalities. So one of the things is garbage in, garbage out. So you need to have good data for you to have good AI. So how do you build better trust through just better data? And finally, there's best practices and ethical considerations. How do we actually design trustworthy AI? Right? Even if you're just using it for like a scientific experiment, how do you do it in a way that people can reproduce it and really appreciate that it's not trying to learn a biased view of things? Okay, so just a quick, primer. What on earth is explainable AI? Today, most of our AI systems, you have training data. You have a machine learning process that takes the data and learns from it and creates a learn function, right? You put data in, it spits out something that you want to predict. Is this a cat? Is this a dog? Is this material gonna collapse? Is it not? Lots of different things you could do. And then it gives you a decision and recommendation. But the main problem is the user has a lot of issues with systems like this. Why did you do that? Why did you give me that recommendation? Why not something else? When do you succeed? When does it work? When doesn't it work so well? When can I trust it? And how do I correct for the error? Well, in a black box system, you don't know how to correct for the error because you don't know where the error came from. So what we're trying to move towards is the notion of explainable AI, where you still have your whole training data, a new machine learning process, but now you have an explainable model with an explainable interface to actually talk to the end user at hand. So you understand why it made a decision, why it didn't make another decision. So you know when it succeeds, when it fails, when you can actually trust it, as well as know when it made an error so you could correct for it. So the other key thing that we're trying to aim for, moving beyond the XAI buzzword, right? Oh, we can make things explainable. You've probably seen those commercials, back then with Watson, where you have like Watson, it's like a screen, and you have big name celebrities talking to Watson, and Watson will talk back. That's sci-fi, right? So what are we trying to get to here? We're trying to move away from a buzzword, from theory into actual insights, from proxy to direct explanations. So one of the things that we've been pushing has been the notion of quantitative explainability. Can we quantify and give rationale to explanations that AI gives you, right? AI can just give you a BS answer, right? It's like, why is the sun red, right? They'll say, oh yeah, because Apollo flies in the sky and paints it red every day. That's an explanation, but it's not quantifiable. Oh, it's kind of bogus. So here what we're trying to move into is a way to actually take and get this quantitative explanation in a way that's a lot more concrete, as well as provide a quantitative justification around it. So for example, here is just a very simple example of an image classifier, right? A deep neural network that can tell different categories of images. What we've done is create something around it that allows it to explain. So in this case, it doesn't say, oh, it's because it's kind of, this area is a little bit more important, this one's less important, how much more, I don't know. Here, we tell you exactly, for example, the plane, it's actually looking at the front, the nose, the top, the winged part of the plane to determine it is a warplane. And not only that, we could actually get it to explain. Okay, great. Like when you stare at that part, why do you think it's a warplane? Because when I look at this part, the model thinks it's a warplane with 98.7% certainty. Otherwise, if it's not relying on this information, it actually thinks it's a parachute with 23.5% certainty. So now you have this much stronger sense as to how it's making decisions. Same thing for the meerkat. It's looking at the face, it's looking at the chest area, and really not relying on anything else. But this is the concrete explanation. Because when it looks at that, it's very certain. Otherwise, if it doesn't rely on this information, it thinks it's an ostrich, right? It makes a very, very stupid decision when it's not focused on the right areas. All right, so that's a very toy example. So why does that matter? So why quantitative explainability? So there's actually very important reasons why we want quantitative explainability. And we're trying to ground in some concrete examples. So one is to ensure that the right decisions are made for the you're like, duh, like obviously you should make the right decision for the right reason. But with AI, you don't know. You want to confirm. So here's an example in a manufacturing scenario. We're using this, we're able to identify the visual indicators the model is using to predict whether a part is defective or not. So here you can clearly see that it thinks the screw is defective because it's looking at the defective area. It thinks the cable bundle is defective because of the straight wires right there. In a healthcare case, what we did was we tried to build a model for predicting lung disease severity. It's able to then tell us that it's looking at the honeycombing patterns in the lungs. It's looking at the ground glass opacities, that so on and so forth, right? So now you could say, oh, okay, great. It's actually performing as it should. And why is this important? Because we also want to identify reasons behind why it makes wrong decisions, right? So we can't just trust things as is. We want to know why. So for example, on the left is the case where for self-driving cars, right? Where the model actually thinks the pedestrian is a cyclist, right? You're like, okay, why would it think it's cycle? Because what you can see, as you see highlighted, is a bicycle that is overlapped by a person, right? So person overlapping a bike means this person is a cyclist, right? So there's logic, there's rationale that seems okay, but it's wrong. So you can then now correct for this kind of behavior. In the middle, the model actually detects, all the pedestrians correctly, but guess what? It was wrong because people got sloppy, right? A lot of times AI is driven by human annotations. You need to teach it how to do things. If the person is wrong and they don't annotate the people, they'll think, okay, I'm wrong. Those are not people, right? So these are kind of things you need to think about. On the right-hand side, if the model makes a misdiagnosis because it doesn't look at the person, it looks at embedded text, right? So knowing this gives you actionable insights into how to correct for your data. Can anyone think of how you correct this? Remove the text. And that's what we did. We removed the text and it started looking at the lungs, right? It's simple as that, right? Another important part about it is detecting the right decisions that are made for the wrong reasons. And this is the most important one that we want to spot, right? Like, it made the right decision. Why is this a useless model? On the bottom left is an example that we worked with somebody. And what we did was we assessed their model. It was getting great accuracy. It was steering all the right, RMSE, root mean squared error, looks great, right? Then we analyze it and we say, take a look. And they threw it in the garbage, right? Why? Because it's making all the great decisions by never looking at the lanes, never looking at the roads, never looking at signs, anything that you would as a person. All it did was look for obstacles to not collide with. So imagine you were just driving and you just, oh, there's a car, I'm going to swerve away from it. There's a post, I'm going to swerve away from it. And you ignore everything else, right? You probably wouldn't go to a car dealership and want to buy that car, right? In the middle of this example, that's his own personal experience. We were trying to build a model to detect, for COVID screening from CT data. Again, very high sensitivity, very high specificity, almost perfect. But of course, we never stopped there. We do explainable insights. And then we saw it and we went back and started from scratch. Why? Because it was able to make all the great decisions by never looking at the patient, never looking at the lungs, never looking at the body, but looking at the type of patient bed they lied on, right? It's incredibly stupid, right? But it doesn't know any better. So again, actionable insight. We removed the bed. It looked at the lungs, right? It's simple things like that, where only explainable insights really help you get to it. And of course, the last one is a situation where working with partners, our data is pristine. It's perfect, right? We clean everything from a data quality perspective, and then we show them this, right? The model was correctly determining disease by looking at all the imaging artifacts. So these are the things you need to keep in mind. And moving beyond that, now that's first order explainability, which is how to try to really understand how an AI makes decisions. Now we're exploring this new notion of second order explainability, which is explaining explainability. Given all the explanations over a wide variety of data, can we identify the core trends, concepts, patterns leveraged by AI to make decisions across all of these different explanations? So here's an example where we did it for a lung disease case. We're like, okay, what are the key things it looks for when determining lung disease? So we took all the explanations and we have it, this second order explainability, analyze it, and it's able to identify, oh, it's looking at honeycombing patterns and ground glass opacity. That's what drives severity assessment. There's lots of other things it could have used, but these are the key things. And we go back to clinicians that this makes sense. Maybe that's what we should focus more about. So it gives humans new insights beyond just understanding how the model makes a decision, but what might be useful when making decisions. So that's why we focus on creating an explainability-driven design framework where you have a generic model with unclear predictions and rationale, and we slowly evolve it with the help of an end user, in this case, a clinician in the loop, that will look at all the insights, give feedback back, the system learns from it, and we end up with a very trusted system that gives, in this case, clinically relevant predictions and sound rationale. Because a lot of times, even talking to clinicians, if you ask them, what are the key defining factors for you making a decision, they can't really tell you, right? But when you isolate, this is what AI is, they can tell you, this is great, this is great, this is great, this is stupid, right? You teach the system back, then it keeps learning what it should look at, what it shouldn't look at, and then highlight things and leverage those that they can. And so here are some use cases around it that you might find interesting. Cool. One is for drug discovery, right? So there's this new trend of leveraging AI to do drug discovery. So here's an example that we created where given a patient's gene expression and the drug molecule, it learns to predict the patient response for a given disease. As I mentioned, personalized medicine. A drug might work for certain people, but might not work as well for others. So how do you predict, given the patient, without giving them the drug, whether or not it's likely to work? Well, you could build a model to simulate and predict that. So that's great. And when you do that, you have no idea what's going on. Why does it work for this patient? Why does it not work for the other? Because the machine told you, all right? So we moved beyond that and we used second order explainability to enable discovery of key genetic factors driving the drug response. So here on the bottom is a big list of genetic factors and their efficacy for helping to make prediction of drug response for a given patient or set of patients. And so what you see in the positive are all the ones that are great as predictive indicators. All the ones that are negative are terrible. What that means is that if you actually use it in your model, it will actually make your predictive performance worse. And so what we did was leverage this whole explainability-driven design and say, hey, these suck. Like, let's not use it. Let's focus on the good ones. And performance went really high. And the explanations made a lot more sense. Another example we used was for diabetic retinopathy, for helping with ophthalmologists to get much deeper insights into a patient's condition. You can predict that this person has diabetic retinopathy, but why? Well, here we're able to show not just, okay, here's why it thinks it's severe, why it's proliferative, but we can also say all the other areas that are either mild or moderate, and this gives them all the information that they need to make a very sound decision, right? Things are not just black and white, right? It's not like this is fine, this is not fine because of this. By giving them all the possibilities and being able to understand it based on what it's showing, then you'll know why it thinks it's mild. It's because, for example, the vasculature here thinks it's mild. There are certain areas that it thinks is negative. Overall, this patient has mild condition. Here's an example where we actually use this for fibrosis progress prediction. So given the patient data, as well their CAT scans, their clinical information, their biochem information, so on and so forth, can we predict their condition, how it's going to progress within a year's time? So in a year from now, are they going to get better? Are they going to get worse? Right? This is very speculative, right? It's all forecasting, right? So doing things right becomes important. One is using multiple modalities. The other key thing is to use explainability to uncover all of the data issues, right? And there were lots. And this is a case where they said the data was perfect. The data was far from perfect. And they even they ran a contest around it. People were doing very well, but they were making decisions for all the wrong reasons, right? Numbers look good, but it's all useless models. So what we then did was help them. We were able to get state-of-the-art performance. We were actually able to beat all the leaderboards. And we confirmed that all the decisions are grounded in the right factors. Why? Because we also got rid of all of the false indicators. Things like, boundaries, right? People are like, oh yeah, look at the boundary, right? That's how I know whether somebody's gonna, have severe conditions down the line. Looking at artifacts. So it went from the top two images to looking at honeycombing patterns, to opacities, and so on and so forth. So it goes from looking at garbage to something that's useful. Cool. And so what we did was we took all this kind of technology and we put it together into a package. So here we made this available for COVID-19 screening. It'll tell the clinician all the reasons why, right? It's looking at the ground class opacities at the lower lung. It's looking at bilateral abnormalities and so on and so forth. Here is why it thinks this patient needs further care. It also allows them to build a big sense of trust with clinicians because they're able to see the results and say, oh yeah, this makes sense, right? I could trust this system because it's thinking in a similar vein as me, right? That's just how humans work. We did this for lung air space disease grading, right? Looking at different zones, identifying where there might be problem. So again, same kind of theme, right? We started off with garbage and we slowly progressed through this approach to having state-of-the-art accuracy, as well as full clinical validation with radiologists, clinicians, and so on and so forth. Right? But again, one of the key things is that all sounds great and all, but one of the key things that's important, and it was actually mentioned in a recent NIST report, is the notion that people often have is AI is magic, right? It just does its stuff. Just dump stuff into it, it'll magically find the right results, right? Hey, I don't know what's the best, structural lattice. I'm just going to dump my data. AI is going to tell me, right? AI isn't magic, right? Garbage in, garbage out. For example, in this case, if it's not in the image, you can't find it. Here's a typical MRI image that you see on the left, right? I've actually done this with students, right? Can you tell me where the tumor is? And for every student who told me where it is based on the left, I'm like, you're just making it up. It's not there. I've confirmed it with a radiologist, right? But that's what they see. So how do you actually improve AI, the trustworthiness and reliability of AI? Improve the data, right? So what we did was, it's a little unorthodox. We're like, hey, existing MRI modalities don't work too well for detecting this type of cancer. We're just going to build a new MRI system, right? Which we did. And so what we got was what was on the left-hand side. Sorry, right-hand side, right? So what you see is in the right-hand side on the, I always say left and right because with radiologists, they often flip. Anyway, so what you see in the big red spot is what the new modality is able to detect, right? It's night and day. And right now we have different clinicians testing it in different areas, right? Ranging from also like prostate, lung, breast, brain, and so on and so forth, and getting really promising results because at the end of the day, data matters. And last but not least is best practices and ethical considerations when building AI. A lot of people think, oh, I'm scientist, I'm just using it to identify, the best drug molecule, the best, crystal lattice, blah, blah, blah. it doesn't have any, real, ethical impact and so on. Right now it doesn't, but down the line it would. So it's important to think about it right now, because even for science, you have to report your results. You want to make it reproducible, right? How are you going to do it? You need to be able to explain and show it. So things to really consider. Accountability. AI make autonomous decisions, but creator is responsible for the outcome. That's a very big wake-up call for a lot of people who created like AI startups in imaging, healthcare, and so on and so forth. And they think, oh, the physician is liable. We're not, right? That's not really the case, right? So understand the seriousness of your deployment, right? Transparency, right? Different AI methods have different level of transparency. So given the right task, you need to understand what's the right level of transparency for you. So for example, you're trying to understand, let's say, crystal lattices. You want it down to the molecular level, right? Makes sense, right? But does that really matter for when a clinician is looking at a patient? Do they really want to know, okay, which of these neurons in a neural network fired? No, they don't care. They want to look, what is it focusing on in the patient's image, right? So knowing that is important. Data provenance, AI is only as good as data used to train it. Really understand the data and the limitations around the data. You have no idea how many people I talk to where they just use and get good performance. And I ask the simple question is, have you ever looked at your data? And the answer is no, but I looked at the performance metric, right? I'm getting 90-something%, so it must be correct. Well, as we clearly illustrated, that's not the case. So don't just trust it. Look at your data, right? Biases, really identify, understand, and mitigate these possible biases that we just talked about. Data leakage, identify predictors that are apparently random. They have no real predictive power, but for some reason, the model uses it. We've seen cases where people use like image watermarks, right? Black bars for padding, like in those movies, right? Embedded text. We have a case where people were looking for molecular information. There was metadata embedded. It was looking at metadata, not the actual data. So little things like that make a big deal, especially when you're trying to publish your, hey, I found like this awesome molecule, but it was just looking at the metadata, right? And of course, class imbalance. That's something a lot of people really need to consider because you might get good results, but that's because your data is highly biased or highly imbalanced. So there was actually a very interesting one where there was a big contest that went on for like cancer prediction. And everyone on the leaderboard, like really quickly, was at 90-something, almost close to perfect, right? And then I looked at the data. I'm like, I could do that in 2 seconds. 90-something% of the data is negative. The little bit left over was positive. I could literally write like 2 lines of code that says, I'm just going to say everyone is negative, and I would get 90-something% accuracy, right? So really understanding what's going on and the imbalances become very important. So just some final thoughts. Backwards is much better than forwards. So again, AI holds considerable promises and potential for clinical decision support in healthcare or just healthcare in general, right? Lots of different good things can come out of it. And for those in other areas like nanotechnology, lots of things like material discovery and so can leverage AI, right? But there's tremendous real world challenges to achieving trusted AI. Just because it can do something doesn't mean it's doing it right and in a way that's reliable, robust, and trustworthy. Fortunately, there's been a lot of progress in trust-driven AI design. Quantitative explainable AI, understanding concretely what it's thinking. Trust quantification, knowing when you can trust it, when you can't, right? Improving just the modalities, the data collection process, as well as really good best practices. So in general, the message here is the benefits really outweigh the challenges in designing and operationalizing trusted AI solutions for healthcare, but in general for any real world applications. So thank you very much for listening.
Wonderful talk. Thank you so much. It's quite provocating as well. It's really thoughtful as well. Any question from the audience, and then we'll go online perhaps. Yes, yeah, there is one. Yeah. Yeah.
So you talked about this for remote communities and such, where you have this AI model that you use to predict this. What sort of computing power, how portable is this? Because from my understanding, computing is very, or for AI is quite resource intensive.
So very good question. So this was not part of my talk because my focus was more on the trusted design. But in my other area of research, it's about efficiency, right? So we actually have a way to create very efficient deep neural networks that run on very, very cheap embedded processors. And we achieve this by not doing it ourselves. We just build an AI that builds the AI that meets the operational requirements. So everything we showed you right now can just run on a very low end processor. It's orders of magnitude faster than anything out there.
Right.
Alex, just to follow up on this, I'm wondering, can these kind of algorithms can also run in our cell phone, for example, to make it more widely available?
Yes, that's correct. So it can actually, first of all, most of our cell phones right now are more powerful than the computers. So that's one. But you can actually, we've actually had situations where we're able to run them on mobile devices, as well as really low cost, like things like Raspberry Pis, anything, even to a microcontroller level.
I had one question, and then okay, Oleg, go ahead. Yeah.
Wonderful talk. So glad that I'm attending here. I have a question. You keep talking about quality of the data. If there is any automated approaches to verify the quality of the data, sort it out, making sure that not just relying on human decision for the quality.
Sorry, I missed the question part.
Okay, the question part is that are there approaches in your field to qualify the data that you're feeding into the system? Some automated way of doing this.
Okay.
And predicting that this maybe data is not good enough.
Very good question. So right now, we've kind of focused more of a human-machine collaboration approach. But that said, all of these, I guess, problems with data was actually unveiled using the actual AI itself. It's able to identify things that it feels are weird or abnormal, and then provide an explanation around it. And so the human in the loop part is for them to actually verify that the AI has actually made the right decision. We've also have situations where we just automate the whole process, and it does improve performance. But the main issue with doing that is for certain use cases, it's perfectly fine. They don't care. Results are better. We scrub the bad data. But there are many situations where you actually have a person in the loop who cares about what type of problem it is, so that they could actually then tackle it at the root cause, right? So for example, if they find out that they've just been imaging things in a really poor way, removing that kind of data might help, but maybe it's a large portion of the data that just gets thrown out. If they knew this ahead of time, and we had situations where they did, then they actually went back to the technicians who imaged it, and they fixed the problem right at the imaging source, and then everything was smooth sailing.
Hi, Alex. Thanks for the wonderful talk. I'm just curious because, as you know, there's a lot of emphasis on EDI, right? To make sure there are no inherent bias. I think this is always going to be a challenge for scientists and healthcare in general. Do you think we'll ever be able to reach a point where the data that's inputted will be eliminated of all biases, or do you think there's just an acceptable level of bias? I'm thinking, that right, the only way to have a perfect AI system is to somehow get rid of all of this inherent systemic type of bias.
And so, very good question. The answer, my own personal opinion, other people might say otherwise, is there is no way to eliminate bias completely. I've seen people try to do all sorts of things, right? Great, what if I just have equal number of data samples for each thing? But then they come to us and we find out, hey, there is bias because one of them is not as diverse as the other. There's no perfect way to do this. Right? So what we've done is help people progressively reduce their bias to the point, given their particular use case, it's good enough for their application, right? So for example, in healthcare, you're never going to get perfect balance across everybody. But through this kind of data control, as well as the way the model actually learns. So different ways we could actually try to, okay, please try to treat this group as fairly as the other group, even though there's a lot more of this group, right? So we do that. But then we're able, and assessment really comes in where they say, okay, great. Now the disparity is maybe 1%. Maybe it's 2%. This is about as far as we could push. And they've also confirmed with a lot of cases where the human who actually usually would have done this manually would actually have greater biases. That's a lot of things that people don't consider, is that our benchmark, which is the operator, could be a radiologist, a clinician, could be, you know, whoever is designing anything, they're not perfect either, right? Go to any like radiologist, like for certain things, huge inter-observer variability, right? You put, and even intra-observer variability, you get a radiologist, right, on a good day and compare it to what they decide on a not so hot day, or before breakfast, after breakfast, it actually changes, right? So when you have an imperfect ground truth and your operator is imperfect, if you could actually minimize bias to be at least on that level, it's very helpful. So nothing's perfect.
Okay, there is one question.
Thanks for a great presentation, Alex. I'm curious about the personalized medicine example that you gave. I think it's a great start to, you know, use genetic information of a person. But there's so many other variables that go into making a person unique. What are kind of the next considerations that you would add into your models? And then second part to that question is it takes a lot of resources to do that for one person. So where do you see doing a study like that or doing an algorithm for one particular person being, you know, feasible or useful?
Yep, good question. So I'll answer the first question first. The way we view it is just at different scales, right? We take a very multi-scale approach and using the right biomarkers at the right scale. So genetic information is great, but it's not available all the time. And it might actually be overkill for certain things. So what we try to do is get a patient's data from the macro level, which is things, you know, heart rate, breath rate, things that you could, anyone, they could even measure it themselves. Then we go next level, which is clinical biomarkers, could be blood tests, it could be, you know, past conditions and so on and so forth. Then slowly work our way down to the genetic level, right? So that's one thing. And so to the thing is, it requires a lot of resources, but not every single problem requires this entire multi-scale stack, right? There are many cases that we work with, for example, for ICU admission, right? We've never used genetic information for that because, first of all, a clinician doesn't use genetic information just to see if somebody gets admitted to ICU. So we try to mimic the level of detail that they need for that particular application. So right now, unless this is a nano conference, so hopefully somebody comes up with great new technologies that really allow you to make your sensing data directly at home, that actually would improve the wealth of data much more. Even right now, with smartphones, right? It's measuring like EEGs, ECGs, and so on and so forth. So using that information already helps. So hopefully down the line, and I've seen people try to do it, is to have a lot more in-home sensing. So again, data, the more data, the better. Then we'll leverage AI to figure out what's useful.
Perfect. Yeah, there's one more question. A lot of questions.
Good. That means everyone's awake.
Thank you. Thank you for your talk. So for the explainable AI, is there like a corresponding downside? For example, is there like a risk that like some markers are like untracked if you were to like disregard data points?
Yeah. So a couple things. One is that it might cause people to think a certain way. We try to avoid it because we don't say like, you know, these are the only things that you should use. We'll just say, this is what the current model is using. These are things that might not be as important, but then you want to then do this whole design process yourself. Like, for example, we don't just eliminate everything that's, you know, not that great. We actually include it and see its overall influence. But having that informed, making informed decisions about how you want to build and design becomes important. So one thing about explainability that is also being talked about right now, that is actually considered, that could be considered as a possible negative thing, is that when you have this much transparency and understanding into a model, there are certain applications where you don't want people to know, right? So one example is for cybersecurity purposes, right? Another one is there's also sensitive information that you don't want to disclose about certain things. It just makes it easier to attack. So there's that side. But for me, in general, explainability, when used correctly for the right applications, becomes very important. Even for attacks, right? We've actually had situations where we're able to use explainability to identify where the attack is. Like what exactly did it do to the actual scene or data that made it think one way when it should be the other. So there's always downsides to everything. As long as you use it properly and design in a way that kind of favors that side, that's all we could do.
Okay, I think, thank you so much, Alex. This was really great plenary talk.
Thank you.